Today's video is about Camshafts 101. Now I have covered this. This is going to be very basic stuff. I've talked about it in some of my earlier videos, and I know the video and sound quality on some of them wasn't great. Plus I've got people joining in on YouTube that just kind of got here and are watching some of the latest videos. And the question has come up about why I draw cams like I do. And I'm going to go over that and just talk about the really basic part of camshafts. What does what. So the regular way people draw cams, or at least it was back when I was younger, is in an overlapping fashion. Basically a 360-degree circle, and your induction and your exhaust overlap at the bottom, even though they don't in real life. This is your true overlap point. And early on I found that to be very confusing. It was hard for me to read, and so I started drawing them a different way. Now in this day and age, a lot of cam guys will do the linear, the flat line, 720 degrees, because remember, an engine goes around twice for an entire cycle. And so you've got 2 revolutions. Everything in a camshaft is in crankshaft degrees. There is no such thing as camshaft degrees. Everything is in degrees of the crankshaft. And so you have 2 rotations. Each rotation, of course, a circle, 360 degrees times 2, 720 degrees. So the linear one models that, and they actually show, usually the lift diagram of the cam, overlap triangle in the middle, kind of at the bottom, and show you kind of the camshaft. That hasn't come along until late these days, more modern age. And I was already doing it my way, and I don't really find that to be quite as helpful as the way I do it. So what I did way back when is I basically took the model that existed and I just expanded it out. This is 720 degrees in a circle. Now remember, a circle can have as many degrees as you want. There is nothing sacred about it having to have 360 degrees. It's just, in normal math, a circle is about that, but it doesn't have to be. So by expanding this out, I actually show the 4 cycles of the engine. We have the induction cycle, the compression cycle, the power cycle, and the exhaust cycle. And that gave me a little better view of what I was kind of looking at when I was trying to learn more about camshafts. And so you've got TDC at the top, TDC at the bottom dead center, of course, halfway. Piston travels down, travels back up, compresses, power, burns, comes back down, pushes back up. Standard 4 cycles. This just kind of shows the 4 cycles. And the reason it helps me is because I actually get to see this at the bottom, which is really important. And I think that people get confused because if they're looking at this doesn't make a lot of sense down here, at least in the way we think. It's technically correct, so is the linear version, but I think this helps picture it because you're actually talking about the 4 cycles of the engine. So up at top is where you wind up with your overlap period. And that's fairly straightforward. That's strictly the time where the exhaust and the intake are both open at the same time. And you can kind of see it and give it a number up here if you're looking at a particular cam so that you have an idea of how much overlap you're talking about. Now, it also kind of lets you see as you pull in the intake center line what's going to happen. If you only change the center line of the camshaft, instead of doing it at 112, you decide you want it ground on 106. well, you can see the center line will be pulled in, the center line will be pulled in, you increase overlap, you open the exhaust later, so you change blowdown, and you close the intake sooner, so you change your inertia ramp. And so it quickly lets you kind of see, okay, if I pull this together, I know what's going to happen. If I rotate the whole thing, that's called advancing a cam. If you rotate it even just 4 degrees, you can start seeing where the events go. If you retard it, you can see what's going to happen to all the events. And so it just kind of gives me a good picture as to what's going on. I can quickly jot some numbers in here and kind of jockey some things around to see where I want to be. And I just find this to be easier, so that's kind of what I'm teaching. The other 2 ways both will work. Like I said, I find it a little confusing. So let's talk about what some of the events do. We have talked a lot about inertia ramp, and the formula for inertia ramp, I have videos on that. The basic principle is you're closing past bottom dead center, and so the mass of the air at airspeed, at a high airspeed, has enough force in it that you can fill past bottom dead center. So you are in the compression stroke. Remember, compression stroke is technically from bottom dead center to top dead center. And so the piston from here to here is going upwards. And this is also where guys will talk about dynamic compression, which I've done a video on that because it's not always what they think. But this is the inertia ramp point, and it kind of is the governing factor for the peak power you're going to make. And so really this event is about being way up here at your peak. That's about peak horsepower, not about bottom end. You're really talking, when you're dealing with this number, about your peak. So if you're talking about bottom end, what are we talking about? Well, a lot of guys confuse overlap and the opening point here for lots of things that don't exist. And the overlap can gain you a little bit at top end through scavenging that last little bit. And again, we've done other videos where we've talked about that. But in reality, the important event is here. It's peak piston speed. And you can calculate it. There's also online calculators. But in general, on a regular V8, you're usually talking somewhere around 74 or 75 degrees after TDC. And the reason that point is important is you've got to remember the piston is descending this whole time to bottom dead center. It is what moves that air. You are pulling on the air. You are basically creating a differential pressure. We call that vacuum. It's a lower pressure than atmospheric in the cylinder. Like I said, we call it vacuum. That's what vacuum is. Now, as that piston descends, it's going to pull. Now, how high a vacuum it generates, depending on how well the airflow comes in. And so your goal is to try and get initially a pretty good fill at this peak piston speed. Now, people mistake it for overlap because as you increase overlap, a stock cam has usually negative overlap. As you go bigger and bigger on camshaft, you are creating overlap. Well, they confuse the overlap with actually the valve exposed at this peak piston speed. Now you need a pretty good opening. Now this can be calculated if you know the displacement of the engine, kind of what RPM you're wanting to work at. You can take the peak piston speed and the area of the piston and calculate a instantaneous CFM at that just bare moment of time of what it's wanting to draw in. And on either side of that, it's going to be a little bit lower. Now, the better you are at being at that flow, at that point, the better the initial fill is going to happen. And this is important. In fact, it's important enough that there's a lot of guys that live on just that one event. They don't know about inertia RAM. They don't understand inertia RAM. They keep tightening up the lobe centers. They keep thinking it's overlap that's doing it, but they're really just getting a better fill at this point. And usually it starts happening at a higher RPM because they're generating more and more overlap, which is hurting the bottom end power. And so they think that that's what they're doing by tightening up the lobe center. Is in their mind they're working on overlap. In reality, they're working on peak piston speed. Now, once you get to the point, say you have a really big head and it has really good fill, and maybe you're not working at that high on RPM. If you reach that point where you meet that instantaneous CFM demand that you get from peak piston speed and the size of the motor, the diameter of the bore, if you reach that point, going more, giving it more lift, more flow, doesn't help you. That's the point, that's all you can do. If you are feeding it all that it can take, you're done. And so a lot of times you will see usually on much bigger heads, that the intake center line doesn't wind up having to be as tight. And you still seem to get good power out of the motor. So that's one thing to be looking at when you're looking at your camshaft. How good is the head? How much lift do I have at this point? How much flow am I going to have? How big is the motor? If you want to calculate that CFM, you can. In normal driver engines, because the ports aren't that huge, and you're not talking about an engine that's going up to 8 or 9,000 RPM, in general, you do not have enough flow at this point. You can't, either you don't have piston to valve clearance up here, so you can't open it faster, you can't necessarily start it earlier, you can't add to this point, so you are usually a little stuck and you can't get enough flow at this point because technically the heads are just not that good at getting that kind of flow. But you'll see a lot of guys build engines that way. A really good head and a lot of flow and a small cam on a tight lobe center with a very low inertia ramp. They'll be down here at 859. They'll be at a really low percentage of what they're using on that airflow. But remember, percentage is really about here and peak power, not about here at fill. If you have that flow, it will help you here. And so that's how you'll see a lot of guys build engines is big induction system, a big cylinder head, lots of flow, big valves, and then not a really big cam. And they're trying to basically just use this event to get as much fill in the cylinder as they can without worrying about inertia RAM or not understanding inertia RAM. So this is important. Now you need to have this one somewhat correct before inertia RAM is going to work. Because remember, the piston is coming down during this whole cycle. That is what's drawing in the air into the cylinder. If you look at a dyno test, they test the exact same cam on the exact same motor, but we did a 106, 110, and a 114 cam with the exact same events. And you tend to find that the smaller intake center line works best. Well, that's because it's working on this fill, and usually they're small enough cams that they weren't really far up here in inertia RAM anyway. And so they might even see a little bit of a gain in peak, but then they'll tell you, well, it did way better down here. Well, that's because it works best, actually, if the air is not moving so fast. So this event is actually your low speed power. It tends to be the power you will generate below your inertia RAM. This is your high, this is your peak, this is your low. And so a lot of times those tighter lobe centers work. This is why when we were testing on the Cadillac, which is a severely induction limited engine for the displacement, you are better off with a very tight lobe center. I mean, we went all the way down to 99 degrees because it kept increasing our flow at this point, and most of the cams for more generalized engines were small. They were way down here. I mean, we're starting to talk about, 215, we're talking little cams. So you weren't getting a lot out of inertia RAM. Remember, this is an exponential curve. As you go further and further this way, your airspeed needs to be good to make it work, but your gains start being more and more. And so that is the basic induction cycle. Now remember, when we were talking about inertia RAM, it is really airspeed based. This works off of airspeed. So a lot of times, if you're building like guys do, where you're talking about big valve, big port, big intake, you'll actually find that in the RPM they're working in, which could be, under 5,000, that they start saying, well, I tried pushing that out and it didn't help. Well, they killed the airspeed by making everything big. And so this is really a balancing act in order to make everything right. And that's why I talk about looking at the formula for inertia RAM and trying to judge what the intake is based on and looking at cross-sectional areas for what it'll flow so that you have a balanced induction. Because if you just pull this way and try an inertia RAM, while it's coming down, it's not getting a good fill here, and you're still playing catch-up before you get down to here. You are not getting a good fill, and you're also not getting a good airspeed. And so this whole thing really needs to be balanced out. Excuse me. You need to be thinking about both ends of it. Just winding the lobe centers costs you here. And if this isn't right, this can never work because you're too busy trying to catch up to the initial point and you can't get that full fill. So both ends of this need to be kind of right. And that's why you've got to look at your center line and what you're doing. And when guys test and they're saying, well, I found the ideal center line, well, they found the ideal center line for the amount of airspeed they had. So for whatever intake they decided to use, which may have been too big, they jockeyed this around and found out, well, if I move this back and I move this up, I actually make a little more power. Well, they're getting a little better fill here, and they didn't have the airspeed to carry this, and in reality, both ends would have done better if they had picked up airspeed. And so this is some of the stuff you need to look at when you're working on camshafts. Now, as we come around, the compression side is pretty straightforward. And like I said, this kind of gets into what guys talk about with dynamic compression, but it's not really what they think. If you want to learn more about that, there is a video on dynamic compression. So once you get it closed, you compress the gas and ignite it, usually right before TDC, so that you have a burn going that produces pressure and pushes the piston down. That's the power stroke. Like I said, this is general, camshafts 101, four-stroke 101, and that's where your power is being produced. Now, this point is your blowdown. And if you look, it's actually in the power stroke. So you are using the burning gas and the pressure that is in the cylinder to start moving the exhaust gas out of the engine. That's why it's called blowdown. The piston is still going down, but you have enough pressure in here to start pushing it out of the engine. And where you decide that's going to be will affect some of where your power is. Now, this particular event tends to help on what I call carryover, and that's the power past your peak. As you go up, you peak, you can go a little bit further. You can maybe pick up another 500 RPM past peak. Well, some of that is controlled by your blowdown. And the reason is, as the engine cycles faster and faster and faster, you are eating up more energy to get the exhaust gas out. If you pull this out a little bit, you will start depressurizing the exhaust side, and that means you have more power that you made already, but you're not having to use it to get the exhaust out. The residual pressure is getting the exhaust out, and that recovered horsepower helps it carry a bit past peak. It doesn't make you any more power. You have already made the power. It's just what you peak at will carry out a little further. And that's technically your blowdown. And it's also going to be louder. Remember, the further into the power stroke, you can actually eat into some of the power if you were to go too far. That's why I try not to go that far. But when you're looking at small cams, you got to remember that technically their blowdown is not anywhere near where it probably ought to be. They are wasting power trying to get the exhaust gas out because they want to keep the duration small enough that it's not going to be loud. Because as you go into the power stroke, you got to remember your mean effective pressure is going to be higher in here, and so that blowdown has a higher pressure pulse, and that makes the engine louder. And so you have to kind of balance where you want to be. Now, my cutoff on most of what I do, like I've said, even in inertia ram, I try and stay below a Z01, which is basically a 256 at 50 cam. Well, on the blowdown, I have an upper limit too, where I don't really like to go above 70 degrees. And I'd rather be back maybe just a little bit before that. As you go too much past 70, you got to start looking at what else you're doing, or you need to be in a lot higher RPM, because you are going to start eating into some of the pressure, especially at low RPM, that can be used to help you. But that's why you tend to favor the exhaust a little bit, is really it's about this blowdown point down here. Now, remember, the exhaust cycle is actually in here. And so the exhaust center line is not happy if you start pulling these together. You decide you want that intake on 106. Well, we'll just have the whole campground on 106. Well, by pulling this way, that doesn't really help you, because your exhaust cycle is actually down here. This is just the very end of it. And that means you're moving the blowdown the wrong way for what we probably want. So you either wind up having to put a bunch more duration on the exhaust side, and you'll run across guys that do this. They'll grind it on 106s, and then they'll tell you, well, I have to add another 20 degrees to the exhaust side, but it's working well now, except for they now have all this overlap, and that's hurting them down here at the low end. So you're better off sometimes figuring out where you want the intake center line, and then maybe having a cam with a little wider lobe separation angle, but sitting in advanced to get the exhaust center line down here. Because this may be happier at, say, 106. Might even be happier at 104 if it's not a real great head. But not only do you have to worry about piston to valve, but that means the exhaust needs to be down here. The exhaust is not happy at 104. It's going to be happier at like 120. It's going to be happier down here because this is where its cycle is. And remember, the center line is basically the peak of the load. So that's where your highest valve opening is. If you can get it down here to where you're keeping the exhaust gases flowing and hopefully moving fairly rapidly, because that's the other thing the blowdown helps, is you increase the exhaust airspeed. And if you can carry that, you can carry it with the center line being more this way. And that's why a lot of times advancing the cam will help. Now, if it's a small cam, a lot of times if you look at a dyno test, the advance, if you advance the whole cam, you're pulling the inertia ram out of it. And then it's like when they test it, it's like, well, we actually made less horsepower by going to 8 degrees advanced. Sorry, I seem to have trouble with my voice today. So that's one thing to think about on your events. Now, the overlap, if you're working on a regular driver sort of car, try and minimize your overlap so you're still okay down here. Now, there is a little bit of power to be gained if it's a tuned header. If you're running a cast iron manifold exhaust system, 2-inch with quiet mufflers, you want as little overlap as you can get. It ain't going to help you at all. You need a tuned exhaust to make this work. You need a long-term, long tube tuned header to really make this work well. And then it'll only gain you a little itty-bitty bit at peak because you have pulled just that last little bit of exhaust gas out. Now, I have moved this event way over here before, and it did just fine. I made sure my blowdown was pushed out a little bit because that made the exhaust cycle work here. You can start to pull a vacuum way back in here if you have everything running right. If it's got airspeed, if the header's the right size, you can actually start pulling vacuum here and get a fair amount of that exhaust gas out without having to push that closing event into the induction cycle. Because for the most part, this section of the induction cycle is not really helping you a lot other than to get the valve open. Once the piston really starts moving down is your main induction cycle. This event, this little window here, is strictly to try and get more open at this point. That is what it's really about. You are going to move so little air as that valve first starts to open that it really doesn't count for airflow. So technically, your induction cycle, even if you're opening back here, your induction cycle is from TDC to your intake closing point. It is not this little bit. This little bit is to help you at that peak piston speed. It's to get the valve open more for when the induction cycle actually starts. And depending on what you're building, most of the time you've got to worry about, piston to valve clearance. You've got to worry about other things about how early you can start that. Plus, if you're starting it way over here and the exhaust is fully in here, that's why sometimes I've pulled this exhaust back here to keep the exhaust at real low RPM from maybe contaminating the incoming charge. As you pull further and further over here, remember the the piston is going to start trying to pull. Well, you still have the exhaust open. And so at real low RPM, where you have no airspeed in the exhaust at all, that can give you a bit of a problem. And that's why sometimes you'll even see pulse back, or not pulse back, but exhaust contamination going past the intake valve and kind of up into the port. You can start seeing the soot line, but that's usually happening way down here. Normally you see it in an engine that might have a lot of idle time but a really big camshaft. It's not really going to happen when it's rocking and rolling, because airspeed changes everything. And so that event you need to think about and try maybe not to have it so far in. This is why most of the time, if you look at camshaft companies, they like doing a center line, say 108 plus 4. That puts it at a 104 intake, a 112 exhaust, pulls some of this out of the induction cycle, and all of those things are good. And that's why in general, companies, without even thinking about it, will throw an extra 4 degrees advance built into the cam. So that's basic camshaft 101. Why I draw it this way, to see it better, and basically what each event is bringing to the deal. This can be your high RPM carryover. This tends to be your low speed, lower RPM fill. This is your high RPM, high airspeed fill. And so depending on what you're building, think about those things. So as usual, I wish you luck on all your projects. That's basic Camshaft 101. I hope that helps. And I'm working on a little more advanced video for the next one. And I'll catch up to you later. So, bye.